Hi, and welcome to another episode of Wonders of Chemistry with Mickey G. In today's episode, I'll be focusing on the concept of isomers in organic chemistry, what they are, and how they can be divided into their various categories. Okay, now isomers of organic molecules have the same molecular formula but different structural formula. They can be divided into structural versus stereoisomers. Let's begin by focusing on structural isomers. This class of isomers have the same molecular formula but different bonding arrangement. Let's look at an example. Let's assume a class of students are given the following molecular formula for a compound, C2H6O, and they are asked to draw the structural formula for this compound. Half the class draw the following structure, while the other half draw the one on the right. The one on the left is called ethanol, while the one on the right is called dimethyl ether. These are termed isomers of each other as they possess the same molecular formula but different structural formula. Both are correct representations for the molecular formula C2H6O and are known more specifically as structural isomers. Okay, let's look a little deeper to see why they are called structural isomers. In order to do this, we will need to count the different types of bonds found in each of these two compounds. The molecule on the left has 5 CH bonds, 1 CC bond, 1 CO bond, and 1 OH bond, while the molecule on the right has 6 CH bonds and 2 CO bonds. So structural isomers have a different number of specific bonds between atoms. Okay, let's move on to stereoisomers. These have the same molecular formula and, unlike structural isomers, have the same bonding arrangement between atoms. The difference lies with the arrangement of atoms in space. Now, stereoisomers can be subdivided into enantiomers, also known as optical isomers, and another class known as diastereoisomers. Now, this particular class of isomer, known as an enantiomer or optical isomer, represents non-superimposable mirror images of a particular molecule. A good example is the amino acid alanine. Alanine here is represented with its 2 mirror images, one on the left and one on the right. Let's look at this a little bit deeper so that you could see what the differences are between both. These molecules are mirror images of each other. Such scenarios occur when at least one carbon within a molecule is bonded to 4 different groups of atoms. Most of the amino acids obey this rule. Here is an example involving the mirror images of the amino acid alanine. Note how both molecules have the same number of specific bonds. However, the molecule on the right is different to the molecule on the left, as it cannot be superimposed. If I attempt to rotate the molecule on the right clockwise so that it matches the 3D orientation of the one on the left, you will see that although I can superimpose the NH2 group, the hydrogen and the CH3 group are out of position. Okay, let's rotate it back to the original format. So we can say that these two molecules are non-superimposable. The one on the left is termed the L isomer. The L stands for levorotary or left turning, while the one on the right is the D isomer. The D stands for dextrorotary or right turning. What's interesting from a biological perspective is that the human metabolism, and more specifically our enzymes, can only recognize the L version of these amino acids. While this is true for amino acids, the opposite is true for monosaccharides, with only the D version being biologically active. Now, if the molecules are not mirror images of one another, they belong to another class of stereoisomer known as diastereoisomers. These include cis and trans isomers. And here are some examples. The one on the left has the substituents, in this case bromine, on the same side of the double bond and is termed the cis isomer, while the one on the right has the substituents, once again bromine, diagonally on opposite sides of the double bond, and this is termed the trans isomer. Another way to work out if it's a cis or a trans isomer is to look at the hydrogens. If they are on the same side of the double bond, it is cis. If they are diagonally on opposite sides, it's trans. Now, the importance of trans versus cis isomers comes to light when dealing with fatty acids, and more specifically, trans fatty acids. These fatty acids are typically produced during the production of margarine and shortening. Shortening is used in the production of pastry and baking cakes and biscuits. Trans fatty acids are associated with an increase in heart disease and type 2 diabetes. Based on this, the World Health Organization have recommended a movement towards eliminating the consumption of industrial trans fats from the diet. So think twice the next time you consume a biscuit or a cake. It may well be high in trans fatty acids. Well, that's it for today's episode. Here is a summary table covering the key points from the presentation. I hope you find it useful. If so, please give me a thumbs up and don't forget to subscribe so that you can keep up to date with my future presentations. Thank you for listening.